Hi, I'm Jerry from the Tureci group at Princeton, and today I'm going to share a talk I originally gave at the 2022 APS March Meeting in Chicago, where I described our general approach to using current quantum processors with finite measurement precision and error rates as reservoirs, reservoirs for computation and learning generally. In particular, in this talk, I'm going to focus on our QASAR algorithm, which is this realization as applied to an annealing system, such as this 25-qubit testbed built by our collaborators at Lincoln Labs, which was the subject of this invited talk at APS. I'm going to describe the application of a minimal version of this device to a non-trivial classification task and describe how we can evaluate the processing capacity in the presence of measurement noise. In the second half of this talk, which should be available wherever you're seeing this, Fangjun is going to describe the dynamics of such a reservoir and its ability to store memory. And Marty is going to describe a specification of this approach to gate-based systems. As some background, reservoir computing is a machine learning paradigm which uses a dynamical physical system, the reservoir, to process generally time-dependent data. It's been successfully realized on a variety of both classical and quantum platforms. But regardless of the specific implementation, the operating principle is that we're going to take this input and encode it in some aspect of the physical system's evolution, thus mapping this input into the high dimensional feature space spanned by the system's, the reservoir's degrees of freedom. We're going to measure a subset of those degrees of freedom, and those are going to form the outputs. And that's the only optimization that's going to occur here, is that we're going to learn a linear set of weights to apply to these measured degrees of freedom, such that they approximate any desired function of the input in its history. So to sort of express this, formulaically, the measured features will depend on the state of the reservoir at the previous time, plus the state of the input at the current time. And this reservoir state is not being optimized, unlike, say, feed-forward or recurrent neural networks. And since we're only training these output weights, this is a very simple convex optimization problem that converges quickly. But despite this simplicity, both for the generally and specifically for the reservoir implementation that we're describing in this talk, you can show that such devices are universal fading memory functional approximators. So you can learn some desired function to an accuracy that scales with the number of measured degrees of freedom that you have. Now, that last point, that more degrees of freedom gives you more computational ability, is why people have been interested in quantum reservoir computers, because they have this exponentially large Hilbert space and thus promise in potentially large number of features. In this spirit, quantum reservoir computing proposals typically assume all the information in the state, so here's the density matrix, is accessible and will use unconditional expectation values as their reservoir features, so the things they apply those linear weights to form their outputs. We're instead concerned with situations relevant to NISQ devices such as this one, whereby only a limited number of variables X are being measured with limited precision, either due to errors, or finite sampling. So we've developed our framework subject to this constraint, and in this talk, I'm going to attempt to understand the expressive capacity in a minimal version of such a system. With that aim in mind, in this talk, I'm going to focus on the nonlinear processing done in a single step of this quantum reservoir's evolution, and thus describe its application to static classical data, such as, say, images, and thus operating this reservoir as an extreme learning machine. Part 2 will cover the dynamics of such systems, so as applied to time-dependent tasks, and the role of memory. Now, if we are instead interested in our thoughts on the reservoir computing of quantum data, where we believe a role for quantum advantage is much more likely, I'd like to direct you to our 2 recent papers, this one in PhysRevX and this one on the archive, as well as these 2 talks also at the same APS. So to operate our annealing system, which is just a controllable Ising lattice as a reservoir, our QASAR proposal involves repeated steps of evolution under an input-dependent Hamiltonian, followed by projective measurement of a subset of the qubits. So this Hamiltonian is going to be described by a set of random parameters, so H, A, B, and J here, with a component that H sub 0 that does not depend on the input, and a component that depends linearly on the input. So here the input is encoded in this either Z or X bias of individual qubits. For each step, the current input is going to be encoded in this Hamiltonian. So we're going to generate a specific Hamiltonian and evolve under that Hamiltonian for time tau. We're then going to measure a subset of the qubits, which we're calling readout qubits, resulting in a polystring, and reset those qubits to 0. The unmeasured qubits are going to serve as some sort of memory in the system, and we're going to update our Hamiltonian to be the next step of the input and repeat this process. So after processing the input for its number of time steps, you would end up with a set of polystrings at each time, and we're going to have to repeat this process S times for S shots to generate a measured distribution at each time. The reservoir features themselves are simply moments of this measured distribution, and in this talk, I'm going to consider reservoirs which use just first moments and second moments as features. So sample means and sample covariances over these measured distributions. But in the other talks, we are going to extend this formalism to higher moments as well. For static tasks, we only have a single time step for the input. It just has one dimension essentially. And thus we can measure all our qubits. So there's going to be no division between readout and measurement qubits here. And to increase the processing capacity of these reservoirs, rather than just using a single random Hamiltonian encoding, I'm going to use P distinct random encodings and pass the input through each of them. So this is going to result in a linear increase in the number of circuit runs that we do, but is also going to give us a linear increase in the number of features that we're able to extract, because I'm simply going to extract the moments and use them for each of these effectively parallel reservoirs. This is also intuitively appealing in that these random Hamiltonians are not optimized for any specific task. So the more random encodings you have, the more likely you are to have an encoding that is effective for any task you give it. So that's our general QASAR algorithm. And I've done a lot of laying stuff out to this point, so I think it's worthwhile to jump directly into a perhaps familiar example. Here we're going to operate this QASAR as an extreme learning machine to perform binary classification on this synthetic noisy spiral data set. So, I have these two spiral arms and there are two different distributions, and the task is to classify a point as being from one of these non-linearly separable distributions or the other. So I'm going to take that point, say this blue point here, and feed it into my reservoir. My reservoir is going to evolve. By feeding it, I mean encoding it into the Hamiltonian of the reservoir. I'm going to then measure the qubits and repeat this process S times and construct my measured moments, and then apply a linear set of weights to those and try to have those weights give me the class label of the distribution that I drew that point from. So either spiral arm 0 or spiral arm 1. This involves essentially inverting this spiral function, which is not actually invertible, to extract this class label C here. And because of that, it's a non-trivial task for neural networks to perform. So here I, tried this TensorFlow plugin that you can find on the internet. And it turned out that I needed to use a decent number of hidden layers and a large number of training epochs using just the raw data to appropriately somewhat learn this spirals distribution. So how does our reservoir do? Well, since I've subjected you guys to like 6 minutes of this talk already, it has to at least kind of work. And indeed here, we're going to look at minimal 2 or 4 qubit versions of this reservoir that use first and second moments as features with up to 10 parallel encodings. We're going to use a limited number of training sets and parameters, as well as dissipation that is consistent with the parameters of that test bed that Lincoln Labs built. So the plots here are showing the classification error over a larger test set. Individual encodings are stars, which you see for 2 qubits are not doing much better than this dashed gray line, which is just doing logistic regression on the input data itself. For 4 qubits, individual encodings do a bit better. However, when I start to add encodings in parallel, so that's the green line for using just first moments and the blue line for using both first and second moments, you'll see our performance improves, and very quickly we're able to get essentially perfect classifications with a very moderate amount of resources here by either adding additional encodings or more qubits. And you can see the feature mapping, which I think is kind of interesting. I've shown it down here for an individual 2 qubit circuit that happened to be pretty close to optimal, just randomly. So it's not quite able to learn the distribution of these two spiral classes. Whereas if I just have 5 random encodings, none of which tend to be optimal or great, they could be all terrible, you still have enough features that you're able to extract the information in the input and learn this spiral distribution quite well. Okay, so that's kind of cool. But we're actually concerned with the performance as a function of the number of shots that we're taking. The measured distribution for finite shots, you can think of as having a correlated noise term that has a power proportional to the number of shots we're taking. And this correlation is actually just the higher moments of the features that you're measuring. So for first moments, it'll be covariances. For second moments, it'll be related to fourth moments. So this is that same 2-qubit system that we saw on the last slide with the infinite shot performance in black. A finite number of shots goes from blue with 10 shots, which is very noisy, to 100,000 shots in red, which is starting to approach the infinite shot performance. And indeed, as you add more parallel encodings, you can effectively recover that. So that's great. You can do better for larger qubit systems. So this is with 4 qubits. And, we can see that, as we add more qubits and more parallel encodings, and additionally, this is all using second moments, we're able to recover the infinite shot limit performance with this constraint of finite shots. And indeed, taking more shots is actually a pretty inefficient way to improve your performance. So if we look at, say, 4 parallel encodings, 10,000 shots here is as good as 3 parallel encodings and 100,000 shots. So you're better off doing more parallel encodings than just taking more shots naively. And we can also look at sort of the role of sampling noise in the feature mapping done by the reservoir. So, for a very low number of shots, it gets effectively washed out by this noise and we're not really able to learn anything. But if we have enough parallel encodings and enough qubits, we're able to use these large number of features that we have to recover the underlying distribution and extract the information in each of these noisy degrees of freedom. So we can quantify the role of things like qubit number and number of parallel encodings and sampling noise by considering a task-independent metric that I'm going to call the nonlinear function capacity. So as a sort of bit of background, if I just fed in random inputs from -1 to 1 into 2 distinct, say, 4-qubit circuits, that's shown here is the features that they generate. So, this is, again, these are first moments on the left, and these are second moments on the right. And you'll see that you get these sort of sinusoidal features that make sense for rotating qubits. And the features are going to be different for distinct moments within a circuit and between circuits. So this is sort of implies that we can try to construct an orthonormal basis of functions from our reservoir features, and that's exactly what I'm going to do. I'm going to use Legendre polynomials, and I'm going to define capacity, C sub L, which is 1 minus the normalized mean squared accuracy at constructing a Legendre polynomial of order L over an input set. And that's being shown on the left here. So say this first circuit is able to very accurately, because if your capacity is 1, you're able to perfectly construct that Legendre polynomial. So it's accurately able to construct Legendre polynomials up to some order, and then it starts to fail. And the second circuit that has different features is better at constructing different Legendre polynomials. And the reason that we're using this as a metric is if I sum these capacities, so I get a total capacity over this entire basis set, it's bounded by the number of linearly independent features in my reservoir. And indeed, if those linearly independent features are noise-free, this bound will be saturated, and that's been shown in a bunch of other works. So for both of these noise-free 4-qubit circuits, it turns out that if I sum these capacities, I indeed will get 15, which is the number of features that they have. What about parallel encodings and sampling noise? So here I have the total capacity, so the sum of those individual capacities for both these same 2 and 4-qubit circuits that we've been thinking about to this point. Both in the infinite sampling limit in black and for finite number of samples from 10 samples in blue to 100,000 samples in red. And individual circuits are against us. And there's sort of 2 things that we should take away from these plots. The first is that this capacity is only growing logarithmically with the shot number. So it only grows logarithmically in the precision in which we can measure these features. And thus, increasing your number of shots is actually a resource inefficient way to improve your nonlinear capacity, which is what we also saw for the spirals task. So this is just a quantifiable metric of this. The capacity does grow linearly, at least initially, with a number of parallel encodings, because you're linearly increasing the number of features that you have. However, different parallel encodings are not necessarily going to give you features that are linearly independent. I'm just choosing random Hamiltonians. So, one random Hamiltonian might have a number of variables that are just linearly dependent on another random Hamiltonian. And indeed, the more encodings you have, the less likely you are to get new independent features, which is why we've actually cut off this study at about 10 encodings. The takeaway here, though, I would say, is that this dashed line is showing you the capacity for an infinite shot single circuit, and which is supposed to be the ideal case. And we're seeing that by using these parallel encodings, we're able to match that performance. And this dashed line is quite larger for 4 qubits than it is for 2. So again, increasing your size of your quantum system and using these parallel encodings is a way to overcome both measurement errors and other sources of errors and noise in your system. So since this is recording and I have time to go into this into a bit of detail, I'm going to mention that we do have a good understanding of why there is this logarithmic scaling in capacity with precision. Okay, so the capacity is actually effectively the number of accessible degrees of freedom in your system in the presence of noise. Accessible meaning above some noise floor. So I can quantify my degrees of freedom by looking at the singular vectors of my unconditional features, so my noise-free features. And if I then look at their singular values, it turns out that a degree of freedom is going to be accessible if that singular value is above some noise threshold. That noise threshold is just the projection of the corresponding singular value onto this noise matrix. So that's what's being shown down here. The projection of singular vectors for different circuits are shown in these bars across, and corresponding singular values for individual encodings in gray, and for parallel encodings from 2 all the way to 10 circuits from, I think, purple to green are stars. So these are singular values, and these are projections of singular vectors onto the noise. And you can just look at this plot and figure out what the capacity is going to be by simply counting the number of singular values above the corresponding shot noise threshold. So that's shown in these straight lines for this 10 qubit circuit, or 10 encoding circuit, sorry. And the logarithmic scaling comes because you can see these singular values themselves fall off exponentially with number. So I need to exponentially decrease my noise threshold, so exponentially increase the number of shots that I take to result in a linear increase in the number of singular values, and thus accessible degrees of freedom that are above that threshold. In summary, I've introduced our proposal for operating current quantum hardware as a reservoir. I've demonstrated the utility of our QASAR algorithm as applied to annealing systems such as this one through its model classification task, and then interpreted its performance by considering the nonlinear capacity of a single evolution step in the presence of errors and particularly measurement noise. We additionally will talk about other aspects of this project in these other talks, which you should be able to access. And if you have any questions on this work, please send me an email. Thank you for listening.